Hey, welcome back. In this video, we're going to talk about stem and leaf plots, which are also called stem plots. In the work of doing statistics, we're going to have a lot of data that we need to organize. And a lot of different times, what we want to do is to present that data in some kind of visual representation. Depending on the type of data that we end up having, whether it's qualitative, quantitative, whether it's discrete quantitative or continuous quantitative, there'll be different methods that we'll want to employ in order to obviously describe the data through a visual representation. One very easy and very useful way to display quantitative information is to use the stem and leaf plots. By the way, this is going to look confusing at first, but once you understand the structure of this plot and how to create these, it is actually very simple. All right, the only complicated thing to understand about when creating a stem and leaf plot is we take quantitative data and we break it into a stem part and a leaf part. And I don't know the history of why we call it these, but I just want to show you. If we have a number, let's say like 58, what we're going to do is to take all of the numbers up to the last digit, and those are going to be the stem. So in this case right here, what we would do is we would make 5 the stem. There's only one digit outside of that far most right digit. And this last digit is going to be the leaf. If we had a number like 273, what we would do is we would take the 2 and the 7, or 27, and we would call that the stem of this data point, and we would call the 3 the leaf. Don't get too caught up in this concept of stem versus leaf at all. It's not really that important. You just need to know how to organize this data with this concept. And again, what you do, this last digit becomes the leaf. So no matter how many numerals or digits you have here, you take the last digit, that's the leaf, and everything else will be called the stem. All right, now that we understand the idea of a stem and a leaf for every data value, what we're going to do is organize these in our table to create this whole stem and leaf plot for all this information. And what we're going to do on this column right here is to list all of the possible stems given these numbers that we have. And again, this will depend on the type of data that you're dealing with. In this case right here, for instance, I could represent 33. The stem part would be this first 3 right here, and the leaf would be this 3. And again, this will end up looking a little bit more complicated, but that's all that we're doing. This is the way we're going to represent 33. We're just separating the tens digit and the ones digit in this case. Very naturally, what we would do then is that we would look at the next category of the 40s. So in the case, I'm looking for what numbers are in the 40s right here. And as I look through this list, there aren't any in the 40s, but we do have a 50 right here. We have 57 and we have 59. And this could represent the only confusion. What do we do if we have multiple numbers that have the same stem? In this case, they're in their 50s, but we have a 57 and a 59. The way that we do that is we're going to write a 5 here for each of those. And over in the leaf, we're just going to list those single digits are the ones digits right here. So this represents 57, and then I'm going to write a 9 after it there. So again, this row right here with the 5 in the stem, and then a 7 and a 9, this represents both the 57 and the 59. This can be where things are a little bit confusing, but once you see the end result, it's really not that difficult. Just remember in every case that each leaf is represented by one digit right here. So every number that we're going to have in this column of a leaf column represents a singular data point. Over here, we just have these stem categories. In this case, these are the tens digits. What I'm going to do now is I'm actually going to now complete this whole plot with this data set because I think seeing the final product will make things a lot easier to understand. All right, here I've finished the stem and leaf plot, and let's walk through this and just make sure it matches our data real fast. Again, this row right here of 3 and 3, that represented just this one data point of 33. We didn't have any of these data points that were in the 40s. We represent that row, but we don't write anything here. Importantly, we don't even write a 0. We'll see when a 0 occurs here in a second. But here, what this represents are the scores of 57 and 59 that we've previously talked about. And now we're in the 60s. These represents, that must be 65 occurring twice And here they are, a 65 and a 65. And then in this row, what this represents is 72, 74, and 75. We have our 75, our 72, and our 74. This row represents an 81, 83, a bunch of 85s, it looks like, and a 87. So we have 85s, there they are. We have an 81, we have an 83, and we have an 87. I haven't gotten that quite yet. And then finally, we should have 3 more left. We have 90, 95, and 98. Here are those 3 scores right there. Again, to touch on the point is that we don't write a 0 in this leaf column for the 40s because that would represent an actual data point of 40. As we had right here, this 0 represents the score of 90 that we have in this situation. A couple of things that we get from this. First of all, this is a very beautiful way of organizing our data so we can quickly kind of see where the concentration or the spread of our data is. Given this quick organization of this data, we can easily see where our data values are like centralized or located. For instance, the 80s are the most represented group here, and most of our data is in the 70s, 80s, or the 90s. All right, that's just a quick introduction. Let's look at one more example where we're given a stem and leaf plot and we have to do a little bit of analysis based on that information. All right, in this example here, we're given that data was collected on the distances of popular hikes in a county. The distances were calculated in miles to an accuracy of 1 decimal place. So this is really important, this statement right here. It helps us understand what this data represents. What we're given is the fact that each of these distances for these hikes is calculated in miles, but with 1 decimal point. What that would mean actually then is the leaf component here, these are in the 10th place or in the first decimal spot. For instance, let's look at maybe this one down here. What this means that this hike, that this is 1 data point, this represents a hike that is 12.3 miles. That means what's being represented here in this stem and leaf plot, given this information about the lengths of these hikes, is that this is the row of all the hikes that are between 6 and 7 miles. So this is 6.5 miles, this is 6.7 miles. Again, it's important, this is a little bit different than the last example. In the last example, we actually had discrete quantitative data, and so we had these whole numbers with no decimal places. We can do that same work if we have this quantitative data that's continuous, where we have decimal places. We can actually still create these. We don't need to represent the actual decimal anywhere, but if we know we have all these accurate to 1 decimal place, we know that the far right digit that we're getting in this leaf column, these represent the decimal place. Again, just to read off one more row to clarify this, is that this row right here would represent 2 different hikes. One of the hikes is 1.1 miles long, and the other hike is 1.5 miles long. Just because it's interesting with this data, I do want to point out that this 12.3 mile data point right here, something we would call an outlier, where we can really see the grouping of all this data up here, and everything is concentrated between 1 and a little over 6 miles. And there's nothing in the 7, 8, 9, 10, or 11 mile range right there, but we have this 12.3 that kind of pops out at the end. We'll talk more about this as we talk about distributions and different data, ways we analyze data, but we would call this data point an outlier because it's so far from where all the other data is grouped. All right, now we can have a little bit of fun. We've been given a task to complete here. We're asked what percentage of the hikes were longer than 4 miles. So we just have 2 things that we need to do. This is really related to that idea of relative frequency, right? But what we're looking to do is count up the total number of hikes. That will be our denominator. And our numerator is the number of hikes represented here that are longer than 4 miles. All right, in order to find out the total number of hikes that are represented here, we just have to count up the number of digits in these leaves. Because remember, when you create this, there's only 1 digit in the leaf category that represents 1 data point. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 hikes all together. Pretty straightforward. And then we want to find the number of hikes that were longer than 4 miles. Well, these are all less than 4 miles. This 4.0, that's actually exactly 4 miles. We're not going to consider that. But everyone after this down the list is longer than 4 miles. That's 4.2, 4.5, 4.5, 4.8, and so on. Let's just count up the number of those. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then to find the percentage, we'll throw that into our calculator, and we're going to get that that's 0.45, or as a percentage, that is represented by 45%.